Now, I would like to have our first speaker of today, Dr. Tae-Hoon Choi, the Chief Executive of Korea RDF. Tae-Hoon, the stage is yours.
Thank you, Ella. Representing Korea RDF, I'm so pleased to host the second Bioconvergence webinar today. Welcome all the participants from Korea and Israel. For this event, IIA and Israel Economic and Trade Office in Israel Embassy in Korea are cooperatively organizing with Korea RDF. I'd like to send my best gratitude to Ms. Anya Alden, Mr. Avi Lufton, and Mr. Yaniv Goldberg for their contribution. Additionally, I am grateful to KDRA and Korea Bio for their support to this event. The biotechnology and pharma sectors, as well as convergence technologies, have expanded considerably in both Korea and Israel. Considering the long time and huge cost for R&D in these fields, projects tend to outgrow the maximum time length and budget ceiling currently offered by usual career program. Following COVID-19, Korea and Israel proved themselves high level of capabilities in the field of health tech, and both sides have a substantial potential in so-called bioconvergence, that is multidisciplinary convergence between the biological technology and the other various technologies, such as nanotechnology, material, 3D printing, AI, big data, IoT, and so on. In this point, MOTI, IIA, and Korean RDF agreed to initiate Bioconvergence initiative at the previous Korea's board members meeting on July 6 this year. Through the discussion among the experts from both countries, 4 subsectors in bioconvergence were derived, such as first, advanced engineering drug delivery and diagnostic systems, for example, bio-nanorobotics. Secondly, advanced therapeutics discovery systems. Thirdly, tissue engineering, for example, 3D bioprinting and cyborg tissues. And lastly, bioelectronics and electroceutical and biosensors and hybrid devices. Let me explain the plan for the Bioconvergence initiative of Korea RDF. That is the first trial of top-down approach in Korea conventional program focusing on specific industrial sector. Next week, Korea will call for proposals in bioconvergence sector, including 4 subsectors that are explained previously. This initiative will be implemented in the frame of the original Korea program, and the funding for bioconvergence will follow the same rules and procedures as the original Korea program with a few exceptions. The exceptions are like this. First, up to 2 projects in bioconvergence sector will be chosen as pilot projects. So if we would receive the proposals more than 2, then there will be competition among the applying proposals in the Bioconvergence initiative to be approved. Secondly, the project will last up to 3 years, and the 4th year is optional without added funding. And last, the grant will be 50% of total project budget, regardless of the evaluation grade, double to $2 million in Bioconvergence initiative. The due date for proposal submission is December 31st this year, and final decision on the approval will be at the first BOD meeting of Korea RDF in the 2nd quarter of next year. I hope that this webinar will be successful to make many excellent joint consortium between both countries in bioconvergence, and Korea RDF will wait for the distinguished proposals in the sector. Finally, I wish that both countries could overcome COVID-19 and return to normal life as soon as possible. Thank you very much for all again.
Thank you very much, Dr. Choi. Now I would like to invite Mr. Yaniv Goldberg, the head of the Israel Economic and Trade Office, the Embassy of Israel in Korea. Yaniv, please.
Yeah, so I would like to thank everyone and to welcome you, and to thank Korea RDF, Dr. Choi, and all the team at Korea, as well as the Innovation Authority from Israel, Yuela and Karina and Anya, of course, and Avi Lufton. and welcome everyone to the second Bioconvergence webinar. The first one took place in June, and we saw it as very successful. And I wish this webinar will be as fruitful as the first one, and even more. I would like to introduce myself very shortly. I'm the head of Israel Economic and Trade Office here in Korea at the Embassy of Israel. And what we do here at our office is connecting between Israeli and Korean companies in all sectors. Obviously, the healthcare and life science sector is one of the most important ones. We connect between Israeli companies and Korean companies, but we also provide scouting services for Korean companies that would like to invest into Israeli companies or just to source in technologies and so forth. We do that by organizing various events, seminar, nowadays online seminars and delegations. And we look forward to cooperate with each and every one of you, be it Israeli companies, most importantly, Korean companies that would like to work with those Israeli companies. I invite you to write us an email. You can see our email address down below, and also take a look at our Korean blog. It's an Israel Trade at Neve blog platform. I would like also to mention that on the end of September, 23rd of September, if all goes well, we will participate with 15 Israeli companies in an exhibition and a conference here in Korea, which is called Biopsy. I guess probably all of you are familiar with that. The conference will be virtual, but if Corona allows, we will have also some kind of a physical presence on the ground. So I invite you all to take a look at our online catalog that will be online starting from next week, with 15 Israeli companies participating and even more. And I would like also to ask Miss Lily Koo to show herself. Lily is working in our team. Lily, are you with us?
Yes.
So say hello to everyone. Probably some of you also know Miss Koo.
Hello.
안녕하세요. And by that, I would like to thank you everyone for participating today. And again, thank you for the organizer, Korea and Innovation Authority from Israel. And I wish you a pleasant listening, and make lots of meetings with the Israeli companies, because that's the most important thing. So thank you very much.
Thank you very much, Yaniv. Now ready to give the brief introduction about bioconvergence. Anya?
Hello again. This is very exciting seminar for us, because this is the first time in our history that we're doing a focused call for proposals around a specific area, not only with Korea, but also with any other country. So for us, it's a first, I hope not the last time. And the reason we're doing this, because bioconvergence is so important for our strategy. And I will very briefly explain why. We really call bioconvergence the future of health tech. This is not just our invention. We think this is an interesting subject to invest. We think this is where healthcare is going. And we think both Israel and Korea have a good chance to take a leading role in this health tech transformation. So, just one word about Israel Innovation Authority. We're a government agency. We spend about $500 million US every year. And our goal is economic. We want to promote sustainable and inclusive growth of Israeli economies through innovation. That is our mission. And we do it through a number of tools, but the one we're talking today is to help enable emerging disruptive technologies. And bioconvergence is such a sector. It's emerging, it's disrupting, and it's going to be a major part of health tech. So bioconvergence is a name we gave to any combination of biology and engineering. So it could be biology and AI, it could be biology and nanotechnology, delivering technologies, gene editing, genetic editing, cell therapies, material engineering, any engineering technologies when combined with biology, we think that will be the disruption in the health tech market. And the reason for that is really this convergence of two different streams that is happening now. And we think if we're very fast, and we're trying to be very fast for a government, we think we can lead this, this convergence. So the changes that the high tech went through, the changes that biotechnology went through in the last 20 years, they're coming to a point where they can be combined. So biology is becoming a very precise science, and AI and data and material science are becoming very available to be combined with biology. I will not go into many examples. I think Dr. Choi showed four different sectors which we felt are most suitable, and I have some more detailed explanations about some of them. But I think the interesting thing about bioconvergence, it really has two different approaches. One is engineering biology. So you take engineering and material technologies and AI technologies, and you apply them to biology. And the other side is exactly the opposite. You take biological approaches to engineering. And you can see today programs that are using biomimicry, using biological processes, looking at how plants and animals operate in the nature and take those approaches into the engineering. So both sides are really colliding to create the bioconvergence. And we are very excited about this area. In Israel, we have very strong multidisciplinary capabilities. We have been very successful in ICT technologies, in AI, in medical device industry. And we think the government has put quite a lot of money, both in the digital side of things, but also in the nanomaterials over the last few years. And we think all of it is coming together, and we can really lead the bioconvergence health tech ecosystem. And the reason we're doing this seminar and this first call for proposal with Korea is because, first of all, we think this is a really good match. We're two countries that have a very similar approach, I think, to industry, very scientific approach to industry, very serious multidisciplinary capabilities. And we think that this is a great area where we can collaborate. And I have to mention, about a year ago, I had a very interesting visit to Korea, and Dr. Choi took me around and introduced me to a lot of people. And it is really exciting, you know, working for a government, things are not always moving so fast. So it's so exciting for me that less than a year after we're sitting here, we're doing this call for proposals. I'm sure we will end up with a very exciting collaboration between Israeli companies and Korean companies. And I'm so very happy and thankful to Yaniv, to Dr. Choi, to everybody involved, and wish us a very successful seminar. Thank you so much.
Thank you very much, Anya, for sharing the information about the bioconvergence. I would like now to invite our next speaker about bioconvergence, Professor San from Korea University. Please, Professor San, your stage is yours.
Hello, thank you, Ola. I'd like to share my slide here. Can you see? Okay, good. Okay, today I'd like to focus on the perspectives or policies on biohealth industrialization in Korea, which can help enterprises of both sides to approach Korean market as well as the collaborate globally together. I have had a chance to get involved in government activities for biohealth policy making over 15 years. Now, actually, I'm a cardiac surgeon. We surgeons do not use brain that much after graduation from medical school. So brain tissue gets smaller and smaller as time goes by. So what I'm trying to say is, this is a presentation of a cardiac surgeon, so please don't expect much and ask much after presentation. When I heard of this seminar from Mr. Choi of Korea, my first question was, how do you define bioconvergence? So I visited your homepage and I found this. Bioconvergence is the name of an industry. I really like this concept. Well, in Korea, we have a little different view on bio issue. Which one is correct? It seems the healthcare technology and the biotechnology are different each other. One is to produce purpose-driven services. The other is to produce a technology-driven product. From the standpoint of view, the technology, healthcare technology is a small part of biotechnology. But when it comes to service, all technologies need to work together to get to the goal. So which one is correct? Yeah, both are correct. Bio and healthcare locate in different dimensions of technology. So the Korean government has adopted the terminology of biohealth for the industry. It is also politically corrected PC word for both MD and PhD, as well as for all government ministries. Yeah, of course, we have a Bioconvergence Research Center at Seoul National University funded by the government. It has focused on the cancer drug development since 2010. Okay, the introduction was too long. The Korean government has addressed 3 industries as the future economical growth engines. They are systemic semiconductor, futuristic car, and the biohealth industry. Last year, President Moon announced national vision for biohealth industrialization. And the government has published 2 reports. One is innovative strategy on biohealth industry. Another is a comprehensive plan for K-New Deal, especially focusing on post-corona situation. I'm going to hand this report to Mr. Choi of Korea for your reference. Let's brief the first one. The strategy was jointly made by 4 relevant ministries. Ministry of Health and Welfare, Science and ICT, Trade, Industry and Energy, Economy and Finance. Yeah, please look at the 3 goals. To increase the global market share 3 times, and to hit 50 billion US dollar export, to create 300,000 new jobs. And there are strategies for each stage of industrialization. You might be interested in this report as well from KeyStep, a leading think tank institute of Korean government. I'll hand this over to. Korea is the country having world's highest R&D investment ratio to national GDP and the number of scientists. This year, total R&D GDP budget is 24.1 billion US dollar, which has increased 18% to last year. The amount of biohealth R&D budget is over 10% of total. We Korean scientists truly appreciate the contribution of Prime Minister Abe from Japan. This is the figure of biohealth industry in Korea. Despite of the lot of R&D investment, we are in a dilemma of being caught in 2% trap. Many investment fall far short of expectations from, with respect to commercialization. We all know that on the way from R&D to industrialization, there are 3 major hurdles. Korean government makes a special effort in the Death Valley. There are 3 major projects for that. One is biohealth cluster as a hardware infrastructure, 2 software infrastructures, research-driven hospital, and the multi-ministerial R&D project. Death Valley is also considered as a funding gap. The government also encourages private investment and tries to build the economy of scale. Of these several biohealth clusters in Korea, Osong has a concentration of healthcare-related government institutes such as FDA, CDC, NIH, KIDI, and so on. It has 4 facilities with a clinical trial center and a hospital. I believe one of the key success factors is the presence of the hospital inside the cluster. This is a basic concept of the research-driven hospital. The hospital becomes a platform to enhance the bidirectional flow between bench and the bedside. It is expected to cover the TRL 3 to 8. And the 3 major ministries have launched the joint project for medical device and the new drug development. They try to build up open ecosystem in each industry. This is the definition of your definition of innovation. I like this very much. I also like the Minnesota definition of innovation. The innovation is the ideas that add value to society should be new, useful, and feasible. I'm going to close my talk with this slide. Convergence is a paramount factor for innovation. When people from different fields get together, there normally exists conflict because the definition of success is different each other. So I believe that the driving force behind the innovation lies in communication-based leadership. We need innovators for the success. Thank you.
Thank you very much, Professor Stein. It was very interesting and very insightful presentation.
I'm going to start immediately. So ABA Bio is a 4.5-year-old company. It was established February 16, 2016. So current number of employees is 16. Actually, we started from 12 in 2016 and rapidly growing company. Main business domain is therapeutic antibody, developing therapeutic antibody for immuno-oncology and neurodegenerative disease. In terms of the financial, through the three different round of investment, ABA Bio funded almost 100 billion Korean won through different rounds of funding. And actually, ABA Bio is listed on Kosdaq market now. And during the IPO, it funded another 90 billion Korean won in December 2018. So ABA Bio's CEO, Dr. Sang-Hoon Lee, he had a BA and MS degree from Korea University, and then he moved to United States and got a doctorate degree from Ohio State University. And following that, he did a fellowship in the Stanford and the Harvard Medical School in UCSF. And he worked as a scientist, principal scientist in the Chiron, AstraZeneca, and Genentech, and so forth, big names of pharmaceutical company in US. And he co-founded and worked as a CSO in another Korean biotech startup called Biomix. And most recently, he worked as a head of the bio division at Hanwha Chemical. And finally, he founded ABA Bio in 2016. We have 6 executives in-house with a very strong academic background and overseas experience. I'm going to skip this slide. And I'd like to introduce the GrabBody platform, which is ABL's main core technology. ABL's, sorry, okay. I'd like to introduce ABL's GrabBody B platform. As you all know, there are enormously high unmet medical needs in Instead of the ABL Bio's GrabBody platform, I'm gonna move to the ABL's pipeline introduction. So ABL Bio's specific focus largely lies in three different areas, namely angiogenesis, immuno-oncology, and neurology. Angiogenesis is our lead program in which we have a clinical asset named ABL001. It is currently in phase 1 clinical trial in Korea, and we have great therapeutic potentials in both gastric and colorectal cancer. For our immuno-oncology program, we have our in-house developed GrabBody T and I, which I will explain in the following slide, but I would like to emphasize that we have active collaboration with other companies such as IMAP, WuXi, and GenScript, as well as academic institutions such as DKFZ in Germany. Lastly, we have an active program in neurology in which we have an in-house developed program called GrabBody B. This is a BBB shuttle that allows for the active penetration of macromolecules such as antibodies to effectively, while safe, infiltrated into the brain. With the completion of these programs, ABL Bio is well positioned to address highly unmet medical needs in both oncology and neurodegenerative disease. I'm going to skip these following three slides, and then move to the slide 9. I would like to introduce GrabBody B platform. As you all know, there are enormously high unmet medical needs in neurodegenerative disease. Unfortunately, there are no effective medicine to address these elements today. Understanding this limitation, ABL Bio has developed in-house a BBB shuttle that effectively delivers antibody to the brain, which we call GrabBody B. We distinguish ourselves from other competitors by engaging a safer and more effective target called IGF-1R. Through this platform, we address Parkinson's disease by applying the GrabBody B onto the IgG that specifically target pathological alpha-synuclein. With a strong in-house technology capability and with strong in-house technology capabilities and with a well-balanced multifunctional team, and through open innovation and active out-licensing activities, we are making a significant stride to develop world-class assets to address this field of oncology and neurodegenerative disease. Thank you.
Thank you very much for the presentation. We would like...
Yes.
Okay, so first, thank you very much for inviting us to the conference. Very interesting talks. My name is Asaf Aron. I'm the Chief Business Officer for Biomix. I'll tell you a little bit about our company in the next 10 minutes or so. So I'll start off with a general mission statement. So as a company, what we do is we develop natural or engineered phage. Now, phage are viruses, but not like the coronaviruses. These are viruses that are very specific to bacteria. So they would kill bacteria, but would be completely inert to mammalian cells. And there are some phage approved for use on meat and cheese and approved by the FDA because of their strong safety profile. And what we're focusing is using these phage in harmful diseases and chronic indications. If you think, for example, about inflammatory bowel disease, so we know today that there are specific bacteria that reside in the gut of IBD patients that are driving an inflammatory response. But we have really, physicians have no good way to treat it. You may say, sure we do. We can use antibiotics to kill bacteria. But there are a few problems with antibiotics. One, there's a lot of antibiotic resistance. The bug we're working on is very antibiotic resistant. But beyond that, we know that antibiotics have harmful effects. Actually, if you give antibiotics to inflammatory bowel disease patients, they actually get worse because you kill all the good bacteria in the gut. And over time, if chronically you'll treat someone with antibiotics, you'll just really ruin his immune system. So it's not an option. So when we use phage, it's a very precise weapon. If you think of antibiotics as like throwing an atomic bomb in your gut, killing everything. So phage are like a guided missile. They will only kill the specific bacteria they're programmed to and not harm the other aspects of the microbiome. And that's exactly the reason and the indications that we're focusing in developing these phage. This is a general overview of the company. So we're about 100 employees, most of them based in Israel. We have a clinical team based in the US. The technology comes from really leaders in the field of the microbiome, both in the Weizmann Institute and MIT. We do all of the discovery of phage in-house. We develop phage cocktails. I'll explain shortly why. We actually have our own in-house manufacturing capabilities. So we actually take these phage products all the way to clinical testing by ourselves. We have 4 programs. Our first one in acne, I'll show you data on it. Just completed phase 1 testing with positive results. We're also working on inflammatory bowel disease and are in discussions under this program with a company in Korea to collaborate on inflammatory bowel disease. And we're also working on liver disease and colorectal cancer. In acne, this product is a gel comprised of natural phage that we're actually pursuing a cosmetic path and have a collaboration with one of the world leading cosmetic companies, and also have a collaboration with Johnson & Johnson on developing biomarkers for IBD. We're fortunate to have really great investors. We have strategic investors like Johnson & Johnson and Takeda, the pharma companies, which each hold 10% of the company. They actually came in a meaningful investment once we had a strong target in IBD, because that's a really big franchise for them. And we have a number of financial investors. To date, we raised around $120 million, 60 of it private and 60 of it publicly. And so total 120. And as of October 2019, are publicly traded on the New York Stock Exchange. So that's kind of the general highlight about the company. So what are phage and how do they work and how do we utilize them? So phage actually look like this lunar landing vehicle or spider with these legs. They're very specific. They bind only to a specific bacteria. Once they bind to that bacteria, they inject their DNA. And within 30 minutes, you have 1 dead bacteria and 100 new phage. Within another 30 minutes, you have 100 dead bacteria and 10,000 new phage. So you can see they're a very potent killer of the specific bacteria they're working on. And we've developed a platform where we do phage hunting. We have capabilities to engineer phage and improve their characteristics, and we do that in some cases. And at the end, we build a cocktail. So for example, for acne, our product is comprised of 3 phage. Why do we need a few phage? To optimize some of the characteristics. So for example, we can have different phage attack the bacteria through different receptors and avoid resistance. We can have phage that work on a broad host range, but all of our products at the end would be a cocktail that would be a very efficient way to eradicate the bacteria, tested in vitro and in vivo. And once we have a stable cocktail that works, we take it into manufacturing and all the way to the clinic. In our pipeline, so acne is our most advanced program. Acne is actually completed phase 1, going to phase 2. IBD is entering the clinic in a couple of months with a first readout at the end of this year. And again, you see there are other programs like liver disease and colorectal cancer. So with the few minutes I have left, I wanted to show you some data from our acne program. So this is a program of a topical gel comprised of 3 phage that kills C. acne. C. acne is a key bacteria driving the disease. It's actually why antibiotics are so widely used for acne. What's unique about this product is that there is a lot of antibiotic resistance. Like in the US, 80% of all C. acne strains are resistant to erythromycin. So antibiotics are really losing their effectiveness. Here, this kills the bacteria differently. It kills 90%, 96% of all bacteria of C. acne, also antibiotic resistant ones. And it also is very efficient at penetrating the skin through penetrating something called biofilm, which is a protective mesh that antibiotics cannot penetrate. So we took this gel, developed it, tested it broadly in vitro, and then conducted a clinical study for 4 weeks. We applied the gel once daily, and we're looking to see if we can show clear eradication of the bacteria using our cocktail. It was tested on 75 females, 2 doses of treatment and 1 placebo, which is the control. And it was a first trial where we could really show in an effective way how our therapy works. So on the left side, you can see safety. So of course, it was very safe. We had no unique adverse events. Nobody stopped the trial because of it, but we know that phage are very safe and exist on our skin and in our gut. But on the right side, you can see how effective the therapy was, and you can see the killing of C. acne, the pathogenic bacteria. So the low dose was not effective, but in the high dose, you could see clear reduction of C. acne on the skin. So you can see really a strong reduction of the bacteria and statistically significant compared to the control. We actually looked also on additional subgroups. So if you look at the population of people with high sebum or higher bacterial rate, you see even more efficient killing on the left side. We saw a 0.4 log reduction within 5 weeks of treatment, which is actually higher than what you see usually in antibiotics. And it's because of some of the high sebum group people have more bacteria, and we could have more interactions with phage and efficient killing. And with these results, we're now pursuing with the high dose, which you see here was very effective. And we're doing a longer study for 12 weeks where we'll be measuring change in lesion counts and also bacterial reduction. So I think I'm up to my 10 minutes. And this program is expected to enter a phase 2 clinical study at the beginning of next year, expecting to show results by mid next year. And following this, because it's a cosmetic route, we don't need to do a phase 3. We expect to initialize commercialization with a cosmetic partner following the phase 2 data. That's it. Thank you very much.
Thank you very much, Asaf, for the very insightful presentation. Now we will.
Okay, great. So first of all, thank you very much for the organizers of this conference to put together a webinar like this. I am Kyung-Eun Kim, and I'm an EVP head of R&D at Cha Biotech. So I have around 9 minutes, so I'll try to use the best of my time to deliver a few messages about Cha Biotech, so we can follow up further for any discussions. So this is a safe harbor statement, the general. And so today my presentation will consist of 4 major parts. So I'll start by giving you some introduction of the company in terms of its general business, leading to R&D competency, followed by project pipeline, and the last slide would be the areas for potential partnership interest. Okay. So a few words on Cha Health System for those of you who may not be familiar. So Cha Health System is a unique organization with a differentiated advantages from other healthcare business. So we have 3 major pillars that are critical for biological R&D incorporated under one umbrella of Cha Health System to create synergies for product development across the value chain. So the first pillar is the one you see on top in blue, university. So we have academic research institute and also undergrad as well as medical school, which will serve as a drive engine for the research projects, which will need to be put into a commercial pipeline later on. The second pillar is the corporation sector, as you can see in the middle in green. And Cha Biotech is a holding company of the subsidiary companies under this umbrella. And then the third sector is a general hospital and medical center. And we have medical centers across 7 different countries, including Korea, US, Japan, and Taiwan, as well as Singapore and Australia, with about 60, so total number of hospitals we have is around 61 medical centers with 1,700 staff altogether. Okay, so on this slide, I'd like to give you an overview of Cha Biotech. Cha Biotech is a biotech company, obviously, and we are specialized in development of cell-based innovative therapeutics to address unmet medical needs. So we choose the lead cell projects based on market analysis and some preliminary animal or in vitro proof of concept data, and then move those selected programs forward into clinical development. So by doing so, a lot of process development as well as clinical development takes place in parallel to enhance the commercial value of a project that is being selected. Okay, and also by leveraging the overseas footprint of Cha Health System that I mentioned in the previous slide, we try to coordinate the local development with the global target. Okay, and on this slide, the history. Okay, so we were, well, Cha Biotech was established in 2002 and went public in 2005. Okay, the first GMP manufacturing facility dedicated for cell therapy production was established in 2011 to allow for clinical development of a product that were in the pipeline back then. Okay, and the last year we built another GMP manufacturing facility, plant number 2, to expand the manufacturing scale to allow for late-stage clinical as well as early commercial launch products of cell-based therapeutics. Based on the technology know-how with production of cell-based therapeutics, we launched Contract Development Manufacturing Organization, CDMO business last year to provide manufacturing service to our partners as well as to lead to business partnerships. Okay, now the core competency. Throughout the last couple of decades of consistent cell therapeutics research and development, Cha Biotech has established core competencies that can clearly distinguish itself. So the first one is expansion and production technology of cell therapeutics that is scalable to support low-cost manufacturing to improve patient access in the market. The second one in green, well, lighter green, is the cryopreservation technology. Especially Dr. Cha, the founder of Cha Biotech, was awarded for a special recognition for his achievement of world's first human oocyte cryopreservation technology back in 1998. Okay, the third core competency is in blue, diversified cell types and clinical indication. So we have built platform technologies, have around diverse cell types, including embryonic stem cells, adult stem cells, neural precursor cells, as well as immune cells from various sources. So they form a solid ground in further expanding the product portfolio as well as serving as a ground for partnerships that we pursue. The last but not the least is the global R&D partnerships. So we already have a few strategic partners, such as Floristem, your local, and as well as Asalis for product development, and also with Paracel by jointly establishing a early clinical research center in Korea 2 years ago. Okay, so we try to fully leverage these core competencies to potentially address the unmet medical needs in the market, especially around the cell therapy products, where the unmet needs heavily resides in the formulation development as well as lowering the cost of goods, thus to improve the patient access. The next slide, a snapshot view of our current pipeline. So we have a diverse types of products in the clinical stage with a few late-stage compounds, but for today, I will just only touch upon two of them, which is cord stem, MSC, mesenchymal stem cell product that is in phase 1, as well as immune cell therapeutics, which is also entering phase 1 this year. Okay, the first one is a CVP-101. It's an NK natural killer cell-based therapeutics with the indication for cancer. And we have already conducted several investigator-initiated trials for GBM, glioblastoma multiforme, and ovarian cancer patients and obtained some positive results. So based on these preliminary or prior R&D, we are moving this program forward into clinic and entering a phase 1 trial for various cancers this year. The next project is called CoreStem DD. It's a mesenchymal stem cell therapeutics derived from cord, the fetal cord, and DD stands for disc degeneration. And it is currently in phase 1/2A in Korea for patients with chronic low back pain due to disc degeneration. Okay. Now, the last slide for areas of potential partnership interest. So we are open for various partnership opportunities, but I just put down a few of them, but it doesn't necessarily mean that we're not interested in other types of strategic partnerships. The first one is we are interested in innovative manufacturing technology to enable large-scale production of cell therapy products. The second is we are interested in technologies which could potentially lead to novel delivery technologies for stem cell culture-derived active pharmaceutical ingredients. And then the third is any genetic engineering technology in order to develop next generation cell therapeutics to further add value of those pre-existing cell therapy products. So that's it for me, and I hope I was on time, and thank you very much.
Thank you very much for the interesting presentation. Now
Okay, so good morning and good afternoon, everyone. Thank you for this opportunity to present today to the Coral RDF. My name is Tanya Gottlieb, and I'm the VP Scientific Affairs at MeMed. And today I'm going to be telling you how we think MeMed actually embodies the concepts of bioconvergence that Anya introduced earlier. So first of all, just a few words about the company. So we're headquartered in Haifa in Israel, but we also now have a US subsidiary. We've raised over $100 million from leading venture capitalists and insurers, including Social Capital and the Li Ka-shing Foundation. We have been the recipient of multiple awards and contracts from the US Department of Defense and the European Commission. And right now we're a multidisciplinary team of over about 50 team members. So MeMed was co-founded by Aaron Eden and Kfir Oved, and they realized from the very beginning that they would need to draw on expertise and know-how from all the different disciplines. So we have team members from the medical field, including infectious diseases, emergency medicine, and immunology. We have molecular biology. We have all the different fields of engineering, software, systems, electrical, mechanical. We also have machine learning and big data, manufacturing and commercial. And as a team, what we're doing together, our mission is to decode the signals of the host response into simple insights that improve people's lives. And what we've actually been focusing on for the last 10 years or so is the signals of the host immune response, and specifically on the following clinical dilemma. So perhaps you take your child or you yourself or your parent and you turn up to the clinician and you have a sore throat and a fever, and the clinician has to make a decision. Do you have a bacterial or viral infection to treat or not to treat with antibiotics? And this seemingly simple problem is actually quite difficult because the symptoms of bacterial and viral infections are often clinically indistinguishable. There are, in fact, many tools available today, but they tend to have limitations across one or more of these dimensions. So for example, the test may take too long until the results come through, so it doesn't fit into the clinical workflow. The test may be difficult to apply or difficult to interpret. Many pathogen-based tests need access to the infection site, which, for example, in lower respiratory tract infections and in ear infections is difficult. Tests that detect the microbe do not necessarily differentiate between colonizers, our flora and fauna, and the actual disease-causing agent, and therefore they can throw up a lot of false positives. And particularly relevant to today, species-specific tests tend to exhibit poor performance in the face of evolving pathogens, such as influenza and coronaviruses. So some of these limitations can be addressed by a different approach. But before I get to that, I want to talk to you, it's been mentioned already by Asaf, one of the global health challenges we're facing today is actually antimicrobial resistance. And a driver of that is this diagnostic uncertainty and that clinical dilemma to treat or not to treat. Because what that leads to is overuse and underuse of antibiotics. It's actually estimated that half of the antibiotics that are prescribed in that clinical dilemma I talked about earlier are unnecessary, and that 1 in 5 bacterial infections go undiagnosed. And John O'Neill, an economist, has predicted that if we don't tackle the rising rates of antimicrobial resistance, by 2050, we'll have over 10 million people dying of estimated GDP loss of over 100 trillion. So Iran and Kfir decided they wanted to take on this challenge, and they wanted to develop a test that would take a few minutes, would require a small volume of blood, and would support the clinician in making better informed antibiotic decisions. And as I mentioned, what we decided to do is, instead of trying to directly detect the pathogen, we decided to decode our immune response to the infection, and in that way to be able to determine if the infection is a bacterial or a viral infection. About 10 years ago, they did a huge proteomic study. The study was called the Curiosity Study. There were over 1,000 patients with different kinds of acute infections, bacterial and viral. And through that study, we managed to identify 3 proteins, a 3-protein signature that performed very well in differentiating between bacterial and viral infections. And the reason that signature performed well is these 3 proteins have very different dynamics in response to bacterial and viral infection. So you have trail, which goes up in viral infection and down in bacterial infection, which is actually a very unusual behavior. You have CRP, which is a classical bacterial-induced protein, and you have IP10, which is a mirror image of CRP, and it's a viral-induced protein. So these 3 proteins together have a very robust performance in differentiating between bacterial and viral infections. So in the first study that I mentioned earlier, called Curiosity, we demonstrated over 90% sensitivity and specificity, and that was reproduced in 2 clinical validation studies that were performed with key opinion leaders across the world in Netherlands and Switzerland. These were blinded studies, and we managed to show the same level of performance. And these studies have been published in these peer-reviewed journals you see here on the right. So having a signature that can perform well in differentiating between bacterial and viral infections is actually only half of the story. Because if you can't perform those measurements and get the test result when and where you need it, it's not going to help the doctor make that better informed decision. So in parallel to the program that I was describing now, where we identified and clinically validated this protein signature, we also, together with the US Department of Defense and the European Commission, have developed and built a new compact, user-friendly platform that we call MeMedKey. So this platform has very high accuracy and precision across a wide dynamic range, because actually the trail protein is present at very, very low levels in the blood, whereas CRP is at much higher levels. It gives rapid results, so we can actually get the test result within 15 minutes using this platform. And we've designed it so that it can be easily transitioned to have multiple different tests from different biological fluids. So I've got here a video, so I'm doing okay for time. I think there we go, just to show you how simple it is. You pop in the cartridge, that's a disposable cartridge. And it's got a very user-friendly interface here, so it can be used by all kinds of different personnel. And we're just going to accelerate this for 15 minutes to get the test result. Okay, here you see that you have a viral test result. Okay, so what was important to say there is that the disposable contains all the reagents and also at the end contains all the waste, and it can be easily disposed of. The machine is very simple and easy to use, requires no maintenance. So this, the development of the test and this platform has been possible thanks to our global network of collaborators, some of whom you see here. And I just wanted to mention a little bit about what we've been doing over the last few months. So actually, the 3 proteins that take part in our signature appear to have also applications that can be useful in managing COVID-19 patients. So some of the work we've been doing over the last few months is clinical studies, collecting samples from patients that are SARS-CoV-2 positive and seeing whether the information provided by those biomarkers. So that is potentially a pipeline product. And thank you very much for your attention. Oh,
thank you very much, Tanya. It was very interesting.
Hello, my name is Haeun Lee. I'm a head of marketing and the business development in Cytogen. It is a great honor to introduce our technology and sharing our achievement with you guys. So the Cytogen is the world leader of the circulating tumor cell-based liquid biopsy. We developed our own automated platform, and then our priority is to capture the live condition of the circulating tumor cell. So using this kind of the property, we can develop the biomarkers for companion diagnostics and therapeutic progress of the monitoring and recurrence of cancers and the indication of identification of new targets using this platform. So I want to introduce the customers and applications. One is for the medical doctors in hospital, try to monitor the condition of the patient after the treatment of the anti-cancer drug. And also pharmaceutical companies need a lot of information after the treatment of the drug for identification of the mode of action of their target and the selection of the patient for their clinical studies. So as I emphasized in the first slide, we capture intact live circulating tumor cell via our Cytogen automated platform. So the reason why I emphasize this property is only live CTC can provide us the DNA and RNA for the analysis of the DNA mutation analysis or RNA profile analysis. Of course, protein can be analyzed in the level of the cell. We will show you guys later about our achievement. So let me introduce the Cytogen's platform, automated platform CTC liquid biopsy. So we have 3 machines for the full process of the analysis of the CTC. One is the smart biopsy cell isolator for the CTC isolation, and the two machines for CTC detection and analysis. One is for automated immunofluorescent stainer, and another one is cell image analyzer. It's full automated microscope. You can easily understand that. So using this platform, we isolate CTC, but our core technology is this HDM chip we developed for isolation of the CTC, because the CTC has a big size compared to the blood cells, so we can capture the size-based the filtration using this chip. So this pore size is really cool and very small. So we use the semiconductor technology to make this, and we also coated the hydrophilic biocomparable coating. We don't need any negative pressure for the washing or whole kind of filtering processes. So with this technology, we can capture CTCs without any pressure or any kind of damages. So we capture CTC as intact live condition. So another one is, I want to share that we do not only capture the CTC only. We can also use other kind of a component in the blood, for example, serum part for the cytokine or chemokine analysis also. But recently, the ctDNA and exosome is really powerful tool identify the mutation of the genes in the cancer cells. And another one is we can also capture as a live condition of the CTC, and the immune cells pass through this filter, and then we can analyze the composition of the immune cells, because recently the immuno-oncology is a major kind of therapy in the cancer field. So we can provide all kind of information of the ctDNA and exosome and CTC and immune cell profile at the same time. So I want to share one example of our achievement working with Daiichi Sankyo in the global pharmaceutical company. So the lung cancer patient has the EGFR, the specific tyrosine kinase inhibitor. This is really the standard protocol for the lung cancer patient. However, this tyrosine kinase inhibitor always has the resistance for this drug. So there is second line for that. If the patient has a T790M mutation, there is second line of the drug. However, there are more patients do not have the T790M the mutation. So we try to find out the specific target or biomarker for these patients, and working with the Daiichi Sankyo, we recruited the 60 patients, and every 4 weeks we collected blood and then analyzed these 4 biomarkers, and then it helps to select the patient and understanding the mode of action of this drug. So let me skip this, and we can also do the single cell level of the RNA sequencing, because we can capture the CTC as a living condition. So I know you guys already know about this kind of high tech and new next generation of the diagnostics using the single cell level of the RNA. So we already achieved to get the result of the single cell RNA sequencing in CTCs. We found out the primary tumors from the CTCs and the metastatic clusters in the blood. So it is really powerful evidence for identification of the CTC, and we can also find out the new biomarker for the cancer patients. So another application I want to emphasize is that this is really famous, the companion diagnostics for the Keytruda, the PD-1 antibody drug. It's really, really powerful drug for the cancer patient. It is very important drug in the world now. So, however, we need to check the expression of the PD-L1, because with this, the protein in the patient cancer tissues, we can treat these patients as this drug. However, there are a lot of kind of problems in the tumor tissue. I put this little way for that. And then we developed to identify the PD-L1 expression in the CTCs, and then we found out it is exactly matching to the tissue tissue results in the PD-L1 companion diagnostic. And then we found out one of the patients shows a little earlier advanced expression of PD-L1. We cannot identify in the tissue examination. So I want to share our reference for the Cytogen Smart Biopsy platform. We analyzed more than 6,000 clinical samples in Korea by collaborating with the major Korean cancer center, for example, National Cancer Center and the Seoul National University and Severance, the 6 major hospitals, and a lot of the cancer types, for example, lung cancer, breast cancer, and the prostate cancer. And also as I emphasized, our whole full automated system is now in the European country, and they work solely in diagnosing the cancer patients. And I already showed you guys the collaboration working with the Daiichi Sankyo. We helped them to develop the first-line drug to treat the cancer patients. So this is the summary. We need the blood to identify the CTCs. However, we can also check all kind of a component from the blood, and we can collect the ctDNA and CTCs, and because we can capture the live condition of the CTC, we can isolate DNA, RNA as high quality, and then we can do all kind of a DNA and RNA the analysis. Thank you very much.
Thank you very much. Now we will move.
Perfect. Thank you, Ella. So I'm Eliron Amir, one of the co-founders and the chief operating officer of the company. Today, I will present you the nuclei. What we do in nuclei is basically analyzing the tumor microenvironment and using this information to match patients with the correct treatment. Our background as a many Israeli startup in AI and software domain is working for many years in the Israeli intelligence forces. My personal background is engineering background, working on AI applications for satellite images. We're a software company, but we're basically in the intersection between software, AI, biopharma, and biology. So we have a multidisciplinary team comprised of clinicians and researchers, for instance, like Alexander Lazar from MD Anderson and Gadi Getz from the Broad Institute. And what we do in nuclei is basically taking the traditional pathology slide, which has been in existence for about 100 years, and analyzing it using deep learning technology. Basically, what we do is structure these images in the way that we can later apply different machine learning algorithm to predict outcome of patients to drugs. Today, most pathology slides are either in just glass slides or are imaged by different sensors, but there isn't a good way to correlate between the different histological features inside the slides with the patient outcome. So basically, our core technology is the ability to analyze the slide with using image analysis algorithms and structure it. We're working on different problems, but the main problems that we're working on is immunotherapy. As you probably know, immunotherapy has revolutionized the cancer treatment world, but only 20 to 30% of patients will respond to immunotherapy. And there's a high need for better biomarkers for immunotherapy. For instance, clinicians in many cases find it hard to choose between different immunotherapy drugs. Payers pay huge amount of money for immunotherapy drugs like Keytruda and Opdivo, which most patients won't respond to them. And pharmaceutical companies fail many of the clinical trials. About 96% of clinical trials fail. Basically, in many cases, due to efficacy problems. So what we do basically in Nuclei is creating a model of the tumor microenvironment. The tumor microenvironment, basically the spatial relationship between the tumor cells and the immune cells, has a lot of predictive power to predict the response to immunotherapy. With current methods like using pathologists and microscopes manually, lack the ability to predict this outcome. So we take the tumor microenvironment and create a model of it based on pathology slides. This is an example of pathology slides. There's a huge amount of data in one pathology slide. And usually this is in low resolution, but in higher resolution, there are hundreds of thousands of cells in each pathology slide. And today, pathologists with their own eyes and microscopes can't really analyze them and find complex correlations between the relationships inside the slide and the outcome result of different drugs. What we do in Nuclei is taking this pathology slide and analyzing it. Basically, we can find the different cells inside the slide and create a characterization of each cell according to different features like cytological features and histological features of these cells. Basically, for each cells, we create a feature vector, creating lots of different characterizations of each cell and correlating the different features that we extract from each slide with a response to a specific drug in order to predict an outcome. The way that we do it, in the most simplest way, is we take pathology slides from patients who responded to drugs. These slides can either come from medical centers, or they can come from clinical trials working with different pharmaceutical companies. So we're getting slides from patients who responded to a specific drug and patients who didn't respond. And the first thing that we do is basically modeling the slides, converting them from a simple image into a structured data. And on top of it, we apply machine learning algorithms to create the signatures which are indicative of response to this drug. We have validated our technology in several ways. One of them is in the latest ASCO conference. They published a paper stratifying different patient populations for breast cancer. We've done it with Alexander Lazar from MD Anderson. And what we do in the company is providing a research platform for pharma companies. Today, we're working with a few of the leading immuno-oncology drug developers in the world, mostly based in the US, some of them in Switzerland, providing them with a discovery platform to help discover different biomarkers which are based on pathology. Our technology can be used in different stages of the drug development process. It can be either used in the exploratory stage, trying to find histological features which are correlated with response. It can be applied in a clinical trials scenario, stratifying patient populations according to the biomarkers that we've discovered. And it can be applied in a companion diagnostic situation after the drug has been approved. Thank you very much.
So I'm Seok Kim from Cytogen. We are a genome editing technology company in Korea. It's a good, I appreciate for the good opportunity to introduce ourselves and find a good partner with the Israeli companies. So that's said. So again, we are a genome editing technology company, and we are operating our company on the basis of a vision to innovate genome using our technology to provide healthier and wealthier life to people and society. So I do not have a general introduction slide for the company as other colleagues did, but we are currently a company of around 60 people. More than half of them are researchers in the field of genome editing and applying this to the therapeutics, which is my field. And also we do have a agricultural genome editing department, which is also another important part of a company. So the total have around 60 people. The company is almost 20 years old, and actually more than 10 years old. The company was founded based on zinc finger technology, so which is kind of like a grandfather in this field. So we've been in this field for a long time. So we, I guess, ran through our own zinc finger nuclease, the first generation technology in this field, up to the CRISPR field, CRISPR technology. And last few years, since we got investment from Korean VCs, we are trying to turn ourselves from the tool developer to the application developer in the field of therapeutics and agriculture, as I mentioned. And I don't think I need to go through the CRISPR-Cas9 technology stage too much. I know other Israeli company introduced CRISPR-Cas9 in last event that you Korea had. So I wouldn't go too much detail, but basically CRISPR-Cas9 is an enzyme composed of Cas9 protein and guide RNA. You can change the power of the guide RNA sequence to freely change the target site of this enzyme, and so you can actually cut almost any site in genome and enable efficient change of the genetic sequence in cell. What's important and might be interest of many of you guys are our involvement in this technology. And so, as I mentioned, Cytogen has been working in this field for a long time from zinc finger nuclease. Unfortunately, we and our founder, Dr. Jinsu Kim, was able to get involved in CRISPR invention very early. So Jinsu filed his first provisional CRISPR-Cas9 technology in 2012 October, which puts us in one of the very early inventors, or like a group who was involved in this IP very early time. Importantly, the first provisional that we filed in October 2012 is the first provisional in the world actually that's showing that CRISPR can function in cell, providing targeted cleavage. So other IPs or provisionals before us all had only in vitro data. So basically like doing all these things in the test tube or like a microfiche tube in reality, I guess. But our provisional had actually cell-based data showing that when we transfer CRISPR-Cas9 with guide RNA with NLS into the human cell lines, we can achieve efficient and specific genome editing. So because of this fact that our IP is the first one in the human cell, basically with the enabling data set, we hope and we are sure that we will be able to secure some of the important claims in the world. And indeed, we have issued claims covering good genome editing, CRISPR-Cas9 mediated genome editing in Korea and also in other countries, including Europe. Some type of issued claims in Europe and Australia and other countries also. And hopefully, we will make other crucial progresses in other countries, including US, where we got good news from PTAD recently. So hopefully, our visibility in this field of IP will be bigger and bigger in coming years. So basically, based on this IP and our experiences in genome editing, we do have expertise in genome editing technology and how to use this genome editing technology in terms of making strategies. And also, we also worked on directed evolution or guide RNA modification and stuff like that. But once we start to work, try to apply this technology for therapeutic system, last 3-4 years, we found that, I mean, it's very important to have capabilities in terms of how to deliver CRISPR-Cas9 into different therapeutic system and therapeutic settings In case of in vivo genome editing therapeutics, where we try to deliver CRISPR-Cas9 into the body of the patient, to specific cell of the patient in the body, we need a good delivery system. So we usually these days use AAV, adeno-associated virus, but also looking for, I guess, chance for the bioconvergence with other material companies to come up with a better delivery system. In ex vivo, I mean, we are working on stem cells and immune cells. I will show a couple of slides about our CAR T technology-related data, but in this field also it's very important to know how to apply CRISPR into different cells. So I think there are a lot of chances to improve this process itself by bioconvergence, which is the topic of today's, I guess, event. In terms of the in vivo, as I mentioned, we are using AAV, which is the most proven gene delivery tool in gene therapy area. We have our own Cas9 IP for covering a whole technology, but also we are working on a small Cas9 also. So we are using bigger Cas9 or smaller Cas9 depending on the target gene and target sequences. We try to deliver CRISPR to eye, liver, and neuro system and have multiple researches, but our current focus is our Charcot-Marie-Tooth 1A, which is a genetic disease in PNS. So I will just have one slide to introduce this program. So Charcot-Marie-Tooth is one of the most common genetic diseases. It affects peripheral nerves. It's a genetic peripheral nerve neuropathy type of a genetic disease. So there are it happens 1 in 25,000. Interesting thing for us is that around half of the patients have same type of mutation. So they are categorized as a CMT1A. The common mutation is actually, unlike the small point mutations, is a large duplication. So the patient have, instead of having 2 alleles, they have 3 alleles, and so they have increased expression of PMP22 in Schuppan cell, which somehow leads to the demyelination or unstable myelination. So the patients slowly lose their peripheral nerve health. So eventually likely to have a walking abnormality, and there are no drug yet. So we are going for this, and we're trying to apply genome editing into these cells and Schwann cells by in a way where we do not completely knock out, because completely eliminating expression of PMP22 can be even more detrimental. So we are targeting regulatory elements of PMP22 to stably downregulate expression of PMP22. And when we deliver CRISPR-Cas9 into the mouse model in a nanoparticle type of delivery in a local way, we show that this very thin phenotype of a peripheral nerve start to get recovered, to have a healthier neurons and healthier myelination, and we can delay or recover muscle loss or recover muscle in animal models. So we are trying to, currently what we are doing is with this proven technology or CRISPR-Cas9, trying to deliver it with AAV in the benign and also severe animal model in rat and mouse currently. So, and we're hoping this data to come within 3 to 6 months time frame so that we can start to move to the preclinical study as soon as possible. Ex vivo applications are usually involving editing of a proven therapeutic cell, which is like immune cell, mesenchymal stem cell, hematopoietic stem cell. In our case, we are focusing, our work, internal work has been focusing on immune cells and mesenchymal, especially CAR T, which has been most focused immune cells. So we already published this data a couple of years ago, so I will just have a couple of key slides. So we are targeting a gene called DGK. These are genes involved in the suppression of the signal 1 of T cell activation, also involved with the CAR signaling. So by knocking out this gene, we expect the CAR T cell will be most stronger. So we'll have an enhanced effector function, but also because there are some well-known negative signal coming from tumors to suppress the immune cell through repression of the signal 1. So knocking out of this gene might provide some resistance to this very important negative signal. So in this CAR T cell-based therapy data, where we look at the cytokine release upon the meeting of the CAR T cells with the tumor cell having the antigen. The white bars are the with or without knockout or like knockout. So by knocking out DGK alpha and zeta in this, as I mentioned, that as expected, we have an increased cytokine release, which means the increased effector function, so likely to have more potent anti-cancer activity, which I do have additional data in next slide. But also upon the in the presence of PGE2, which is a negative signal, or a TGF beta in control, CAR T cells has a very significant downregulation of this or a reduction of the cytokine release upon the meeting with the cell line, the cancer cells, showing that indeed these negative signals are repressing T cell activity. But DGK knockout T cells are partially or almost completely resistant to this phenomenon, showing that maybe in this DGK knockout might render a better function in TME, which has been discussed in previous presentation also. So just to confirm the activity, enhanced activity of CAR T, we did a mouse-based xenograft study where it again we replicated the data where the control T cells or control CAR Ts cannot repress the tumor growth as well. But TGK knockout CAR Ts are repressing, killing cancer pretty well. Correlates with also the TIL in the tumor when from the extracted tumor that we analyzed. So basically, it shows that we can actually knock out genes pretty well in CAR T, and when you have good target gene, you can enhance target activity and potentially also the function in TME also. So these are some of the studies that we've been doing, and there are additional programs. But basically, I wanna end quickly this presentation with my understanding of or interest in the partnerings. Of course, in the side of the delivery in vivo and ex vivo, new type of delivery tool, especially in a non-viral type of delivery tools, are very interesting opportunity for us. Also in ex vivo, we are currently using electroporation, but better electroporation, or even like fluidics type of microfluidics type of delivery tools that currently are being entertained are very interesting. So we are also interested in those type of opportunities. To the left side, I mean, in terms of the more of a synthetic biology type of approaches to get better expression system for CRISPR-Cas9 to have Cas9 expressed more specifically in certain cells or induced by certain cues will be very interesting. Additionally, as I think a lot of scientists interested in predicting CRISPR-Cas9's off-target, on-target activities, very interesting field. And there are some AI-mediated prediction tool, but so far for us, never it worked as well. So I mean, having opportunity to have better AI-mediated prediction type of collaboration will be very interesting for us. Thank you very much, and I'll be happy to answer any question if you post it later. Thank you.
Thank you very much. So thank you very much for listening, and we hope to see you soon in Israel or Korea when the COVID-19 will allow it. Thank you very much.